Okay, so we're going to finish up our intro to energy notes in this video. We are on page 7 of the lesson 3.1 energy and thermochemistry notes. Okay, so here we have a sample problem to help us practice thinking about the system and how heat and work go in and out of a system. As remember in our previous videos from before our test, we said we have to define the system. That's where things happen, and the surroundings is whatever is around that. So here we have a system receives a deposit of 50 joules of work from the surroundings, and it loses a withdrawal of 85 joules of heat to the surroundings. What is the magnitude, that means the value, the number value, of delta E, and what is the sign of delta E? So we know that our internal energy, our change in internal energy, is going to be equal to the heat that goes in and out, plus the work that goes in and out. And we're using a safe as an analogy for the system. Our Q, our heat, was what? What happened to our heat? We lost heat. I should really, if I had more, I would circle that. We lost heat. So here we're showing that heat with arrows coming out of the system. So if heat is lost, its sign is going to be less than 0. We have that. If you look here, for Q, for heat, if heat is lost, you're going to use a negative sign. I'll shrink this for a second. So our 85 joules are going to be minus 85 joules. Now we have to think about the work. I didn't mean to cover up the problem. Irritating. Anyway, there we go. Our work is deposited. We get a deposit of 50 joules of work from the surroundings. And here's a picture showing work being done on the system. And let's look at what the sign would be for that. For work, when work is done on the system by the surroundings, the sign's going to be plus. So the sign for our work is going to be plus. Oops. So we're going to add plus 50 joules of work. And this was a mistake again. What's wrong with my brain? This was delta E, okay? I was substituting in over here. I had delta E equals Q plus work, and over here, good God, what I was attempting to do was substitute, here's delta, oh come on, here, let's fix this, I had delta E equals Q plus work, here, this should have been delta E, and I substituted in for Q, the minus 85 joules, I put the correct sign in front, I substituted in for work, and that was positive. We figured that out looking at the arrows and also the chart. So our delta E calculation, then we would go delta E equals 50 minus 85. It's going to be equal to minus 35 joules. So that this system had a net loss of internal energy. Net loss of 35 joules of energy. That's what that tells you. In this sample problem, we're going to, I think about work. It tells us a fuel is burned in a cylinder. The cylinder is equipped with a piston. We have pictures of this. I'll add one right now. Okay, I've added a picture to help us here. So our initial volume of our cylinder, we're burning a fuel in our flask here. Here's our fuel. We have oxygen in there. We're going to burn it. It will, when something combusts or burns, it makes carbon dioxide gas and water gas. So as this burns, it'll make a gas, and the gas is going to expand and push this piston, this is the piston, up. The initial volume of our cylinder is 250 liters, 0.25 liters, so I wrote that over here. And the final volume after the reaction is done is 0.980 liters. It tells us that right here. So I wrote that over here. If the piston expands against a constant pressure of 1.35 atmospheres, so that would be the atmospheric pressure equals 1.35 atmospheres, then what is the work done in joules? So we have an equation that could figure that out. I'll write it down. We know that work equals the opposite of pressure times change in volume. So let's substitute in the opposite, our pressure up here, it tells us is 1.35 atmospheres. 1.35 atmospheres. And our change in volume, oopsies, we probably have to do a side calculation for that, so we'll do it in black. We have our change in volume is going to be equal to our final volume minus our initial volume. Our final volume is right here, 0.980 liters. 0.980 liters minus our initial volume is over here, 0.250 liters. So we can make that calculation. So our final, our volume change is 0.730 liters. I left it as to the thousandths place because we're doing subtraction, and we have, they're both go to the thousandths place, so that should be our significant end. So we're going to put 0.730 liters here. Now I'm going to get myself some more room and then multiply these, because multiplied. Okay, so now I have more room and I can figure out the work, because the work is the opposite of 1.35 times 0.730, and that is negative 0.9855, and my units are going to be atmospheres, liters, multiplied by each other. A weird unit, eh? So it tells us in the problem, somewhere on your paper anyway, that 1 atmosphere liter, or 1 liter atmosphere, equals 101.3 joules. So the last step, we're going to convert our units here to joules. We're going to convert this to joules because this doesn't really look like a unit of energy, even though it is. So to convert, we're going to take our negative 0.9855 liter atmospheres, and we're going to multiply them by a conversion factor that we get from our paper. If we look at the problem, up here, look up here, it tells us 1 liter atmosphere is 101.3 joules. Oops. So let's put that in. We have 1 liter atmosphere is equal to 101.3 joules. Then we're going to multiply. Our liter atmospheres cancel, and in joules our answer will be 0.9855 times 101.3, or 99.8. We're working with how many significant figures here? 3, right? So 99.8 joules is our answer, and it's negative. Negative, and I'm going to circle my answer. Negative 99.8. Finally, we're almost done with this. So we said that our enthalpy in the previous video is equal to heat at constant pressure, because we went through some sort of, we said delta E is equal to Q plus work, and we said that delta H is equal to delta E plus P delta V, and we said that work is equal to minus P delta V, and after substituting in blah blah blah, this was all in the previous video, we said that delta H is equal to heat. So it's since it's equal to heat, as long as the pressure is constant, whatever the sign is, if our heat transfer is exothermic, the sign of our enthalpy will be exothermic. If our heat transfer is endothermic, the sign of our enthalpy will be endothermic. And just to refresh your memory, exothermic for heat, we write a minus sign. Endo, the convention is we say it's positive. So where it says enthalpy change, that this is what you want to write down. For enthalpy, the signs are going to be the same for heat. If enthalpy is this is what you write down at the top of the page. The signs are the same. So let's do this little sample problem. Not that. This. No. 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 There we go. So we're going to indicate the sign of the enthalpy change in the following processes. And it tells us they're carried out at constant pressure, which is very important because otherwise this relationship would not be true. So we have an ice cube melting. And the reason we're doing this sample problem is we're learning how to think about the system versus the surroundings. In an ice cube melting, here's our ice cube, and it's melting into a nice little puddle. Our system, in this case, is going to be the ice cube. The surroundings is the air around the ice cube. In order for the ice cube to melt, heat has to come into the ice cube, which means heat is entering the system, coming into the system. So this will be endothermic. So therefore, it will be endothermic. So the sign will be positive, which I think was the question. Delta H will be positive. The next one, we have B, we have 1 gram of butane is being combusted in sufficient oxygen to give complete combustion. So we have 1 gram of butane plus oxygen is going to make CO2 plus H2O. In this case, go away, the system will be the butane plus the oxygen. When you combust anything, it gives off heat. We'll get a red arrow to show heat. So when we combust this, heat will be released from the butane and the oxygen. This is our system. So heat was released from our system into the surroundings because we're burning the butane. So therefore for B, go back to purple, for letter B, delta H will be exothermic because heat was released. So the sign will be negative. And that is the end.